energy levels, built-in voltage, and open circuit voltage. When we make a solar cell, we use a semiconductor absorber and attach selective contacts, which is a material with a large work function and another one with a low work function that will make the contact to electrons and holes. Now, this difference is built-in voltage, the difference between the work function of the contacts. And since the system is going to come to equilibrium, the Fermi level will become flat. And one possibility to achieve the equilibrium is that the whole initial built-in voltage stays as a difference of electric potential in the semiconductor, and then this will form an electrical field in the semiconductor. But another possibility is that a part of the built-in voltage is absorbed at the contact, like a dipole layer. Then the electrical field across the semiconductor will be smaller, and eventually we can have the whole drop at one contact, and then the bands will be flat, and still we will have the semiconductor in equilibrium with the contacts. And then there are different ways depending on how the material in the center achieves equilibrium with each of the contact layers. We can find the depletion layers. There are different possibilities. Now, in practice, this is more complex. This is an example of a perovskite, which could be N or P type according to the doping. And then the selective contacts are composed of different layers, TiO2, ITO for the electron contact, gold and organic spiro for the hole contact. And this will come to equilibrium, and then all the Fermi levels will be aligned, implying that there is a difference of the vacuum levels with some dipole drops across the interfaces. So here the built-in voltage will be the initial difference between gold and ITO. This is about 0.4 electron volts, so that this difference in the end is 0.4 electron volts, and also this one. This energy difference can be measured in several ways. It's very interesting, the Kelvin probe force microscopy. It's going to track the local vacuum level and show where the electric potential is constant and the band more or less flat, and where is a drop of the potential and accumulation of space charge. So this is one example showing in dark the equilibrium of potential, and under illumination the photopotential is reaching this value with respect to the other electrode. It's also interesting that tracking the potential across the cell is giving us a picture of where is the charge separation in these conditions, because the second derivative of the potential is the local charge. And then we can see that there is a strong separation of charge at each contact, but in the middle of the perovskite, the band is almost flat. We analyze the significance of the built-in voltage and the distribution of potential for the photovoltaic operation. So this is a first model, still very popular in many analyses of photovoltaic systems, in which, as we said before, the built-in voltage is transformed completely into an electrical field, and then this electrical field is supposed to separate charge so that electrons in the conduction band are going one way and the holes in the valence band are going the other way. As the voltage is increased, the band is becoming more flat, and finally, when it is flat, it will stop the production of photocurrent. So this is the operation of this model. We can see here the initial situation, and then we arrive at flat band, which is the VOC, exactly equal to the initial built-in field. And we can apply a further forward voltage or a reverse voltage. And in any case, we modify the electrical field inside. Of course, this primitive model doesn't take into account the distribution of Fermi levels. As we have explained before, the operation of the solar cell, especially concerning the photovoltaic, is associated to a separation of Fermi levels by illumination in the absorber material. And then there are selective contacts that take better or worse the separation of the Fermi levels. In this case, the electron selective contact and hole selective contact are tracking perfectly the internal photovoltaic. So that in the operation of the solar cell, we have to separate things. So one is the internal separation of Fermi levels in the absorber, which is governed by illumination, recombination, etc. And another important aspect is how well the selective contacts extract, or to what extent the selective contact extract this voltage by tracking the Fermi levels or if there are losses. So this is one example. In the first case, we will have a separation of Fermi levels, which is the internal VOC, and the contacts are following very well for holes and for electrons the internal separation of Fermi levels, so that the whole internal separation is converted into VOC. In the second case, the electron selecting contact energy level is below the other one, so that it's not reaching the equilibrium with the internal Fermi level. So there is a voltage loss here, delta V. And then in the second case, the voltage will be smaller than in the first one. So the properties of the contacts are essential to extract the photovoltaic. When there is a modification of photovoltaic in a type of solar cell, here comparing two different perovskite solar cell, a control device and a treated device, we can analyze the energy levels to investigate if the contact is due to the absorber properties itself or to effects of the contacts. Here, by seeing the modifications of the energy levels by UPS, of the position of the bands, and the change of the Fermi levels, we can make these plots and see that in the second cell, all the levels have gone up and the Fermi level is closer to the conduction band, explaining the increase of the photovoltaic just by the properties of the bulk semiconductor. But if the contact is deficient, then it will decrease the VOC. Here in the left case, we have that there is a very good extraction of the voltage of the internal Fermi levels at the two contacts, and at the right side, the whole selective contact is producing some bending and not contacting well the Fermi level of holes. So this is decreasing the internal separation and the external VOC. We have seen that there can be a decrease of the internal separation of Fermi levels, or the transduction of the Fermi level to the outer contact. And another question is if the initial built-in voltage is determining the final possible VOC. In this case, the electron contact energy level is too low. It cannot reach the internal Fermi level, or maybe it can reach it, even if initially it was too low. This has to be investigated. This is a representation of the previous example. Before making contact, this is the electron selective contact that will come down here, forming a drop of the vacuum level. When we illuminate the solar cell, it will go up again, up to the situation where it started. And then here we have the voltage deficit. And the question is, this contact can go higher? Yes, if it goes higher, however, there will be an upward bending here. So this is not favorable for extracting electrons because they find an upward barrier. But anyway, maybe this can happen. So then the contact will be equilibrated to the internal Fermi level regardless of the initial energy. This depends on the material properties. Here we show an example for a dye-sensitized solar cell. Here is a TiO2 and electrolyte. This is the band of TiO2, and this is the FTO contact. When the photovoltaic is created, we are going to generate electrons up here, and the Fermi level rises, and the barrier at the FTO is going to decrease up to the initial work function of the FTO. If we go higher, then in the end we will form an opposite barrier that is opposing the extraction of electrons. This is the problem of going to a VOC that is higher than the initial built-in voltage. Here is a final example in which we have a MAPI solar cell indicated here. The conduction band is at 436 electron volts below vacuum, and we are using 3 contacts for the TiO2. The energy levels are very well aligned to the conduction band of the MAPI here. And we get a good photovoltaic of about 1 volt. But a solar cell is made with FTO that is much deeper, almost 1 volt deeper. And it turns out that the FTO can also equilibrate the Fermi level of electrons up here and provide also a good photovoltaic.